This video is on Newton's first law of inertia. I'm Mrs. Estock. Let's get started. Before we begin discussing Newton's first law of inertia, let's take a moment to change the way that we approach our line of thinking when it comes to Newton's laws. If you approach these thinking about what happens when you stop applying a force to an object, imagine that you're pushing on an object and you stop applying a force to it. What would you imagine would happen? Well, most people think, well, if I stop pushing it, its natural tendency is to eventually slow down and come to a stop. But what you're not considering here is that there is a force that's causing it to come to a stop eventually, and that is friction. It's not the natural tendency of the object, it's friction acting as an unbalanced force, causing it to change its motion. Imagine, though, what if, when you stop pushing that object, there was no friction? What if there was no unbalanced force to slow it down? Therein lies the natural tendency of objects. Any object with mass has a natural tendency to want to keep doing what it's already doing. In other words, its natural tendency is to maintain its current state of motion, if and only if there is no unbalanced net force acting on it. So if there was no friction, an object in motion would tend to want to stay in motion, maintaining its constant velocity motion. And only an unbalanced net force will cause the object to change its state of motion, to speed up, slow down, or change direction. This is an important idea to start thinking about as we begin talking about Newton's laws. Thinking about the example we just used, if you're pushing on a physics textbook to get it to slide across the table, and all of a sudden you stop applying that force, it will slow down and come to a stop, but that's because friction is causing it to do so. In the absence of a force of friction, that book would continue to slide across the table with the same speed and in the same direction forever, until some unbalanced force causes it to change its motion. We will be able to take a look at this type of motion in class using hover pucks, where they're hovering above the surface using a tiny little layer of air. So you have the upward force of the air that's balancing out the downward weight force of the puck, and without scraping against the surface, as long as there is minimal air resistance, you will get constant motion after you stop pushing on that puck. Let me show you a quick video example. Where did I put it? Of what this will look like, and we'll get some hands-on. That's a nice little pose the guy is doing there. But we'll get an example of this in class as well, so you'll get to get your hands on this in a couple of days. So you could see there that the puck, once you gave it a push, kept moving with constant speed. So once it was in motion, it wanted to stay in motion. Without friction there to slow it down, it would keep moving at a constant velocity. This brings us to Newton's first law, which is also called Newton's first law of inertia. It tells us that an object in motion will stay in motion, and an object at rest will stay at rest, unless acted on by a net external force. And if I were to summarize that in a simpler sentence, I would say that objects tend to keep doing what they're already doing. Here we have a little diagram to help us figure out what causes an object to either stay at rest or stay in motion. If and only if the forces on the object are balanced, in other words, if it's in a state of equilibrium, objects at rest will stay at rest, and objects in motion will stay in motion. Notice that in both cases, the objects have an acceleration of 0. If an object is not accelerating, it is either at rest or it's moving with a constant velocity. Also a reminder that velocity is a vector quantity. So a constant velocity means that it's maintaining a constant speed and a constant direction. Here's something else to think about. If we were to expand on our hover puck example, this is a famous physics thought experiment where, let's say you were in outer space and you throw a baseball into the vast void of outer space. According to Newton's first law, if there are no net forces acting on that ball, it's going to continue to move in a straight line at a constant speed forever until it encounters some force that changes its state of motion. Remember, an object in motion tends to stay in motion. And if we think outside of the box, outside of the confines of our experience on Earth, something in outer space like this, we can see how Newton's laws would cause that ball to stay in motion forever until it encounters some net external force. So now we know all objects tend to want to keep doing what they already are doing. This resistance to a change in its state of motion is something that physicists define as inertia. The more inertia an object has, the more its tendency is to resist a change in its state of motion. Well, when does an object have more inertia? Picture this example. Imagine up on the front table I have 2 buckets, one empty and one full of sand. If I wanted to give a small push equal in size to each bucket, which one is going to be easier to change its state of motion? The empty bucket, the one with less mass. The bucket that's filled with sand has a greater tendency to want to stay at rest. That's because it has more mass. The more mass something has, the more inertia we say it has. The more of a tendency it has to resist a change in its state of motion. So if we define inertia as the tendency of an object to keep doing what it's already doing, it's really directly related to its mass. The more mass an object has, the more it tends to want to keep doing what it's already doing. So objects with small mass have small inertia, and the larger the mass of the object, the more inertia it will have. So to summarize Newton's first law of motion, also known as his law of inertia, it says that an object will not change its motion unless acted on by an unbalanced force. If it's at rest, it tends to stay at rest, and if it's in motion, it tends to stay in motion. Think back to our original example with the hover puck to really get a good understanding of what Newton was saying here. Remember, it's not the natural tendency of an object to change its motion. It has to be some unbalanced force causing it to change its motion, like the hover puck. If the hover puck is hovering without friction, then it's going to either stay in one place, or once you give it a push, it's going to keep going at a constant velocity. Another thing we learned is that objects with more mass have more inertia. That's a direct relationship between the two. And the more inertia something has, the more it wants to maintain its state of motion. And what we'll look at next with Newton's second law in our next lecture is that if something has more mass, it's going to require more unbalanced force to cause a change in its state of motion.